Hello and welcome. Today we'll take a look at this kind of energy line effect on a sphere. There are many ways in which you can achieve the result, but my first instinct is always to use VEX as the primary attempt, let's say. So let me start by explaining a few geometric concepts. For our simulation, we just need two kinds of motion, the horizontal one and the vertical one. So a particle can start horizontal, then switch to vertical, then switch to horizontal, switch to vertical, and so on. So it's crucial for us to be able to create a circular motion. And on a plane, let's say that this is maybe the x-axis, and this is the y. The parametric equation of a circle is cosine of a parameter t and sine of the same parameter t. And this is the equation for a circle of radius 1. If we want a generic radius r, we have to multiply both the components for the radius. Now, the problem is, this is an equation for a particle starting from the x-axis. What if the particle is somewhere else? Let's say here. In this case, we have to calculate the angle with the x-axis, let's say alpha, and the equation becomes t plus alpha and t plus alpha. Now, the last step is to calculate alpha. And we know this point here because it is our p-attrib. And we know the x-axis is 1, 0, the unit vector. So how to calculate alpha? We can use the dot product, for example. Let me create a new. Let's say we have two vectors, A and B. And as you know, the geometric interpretation of the dot product is A times B is equal to the length of A times the length of B times the cosine of the angle between them. Okay, so A is our unit vector, so A is equal to 1. If we divide the dot product with the length of B, we get the cosine of alpha. If we take the inverse of the cosine, which is the arc cosine, A cos, we get alpha. Now, there is a problem with the dot product, which is the symmetry, basically. So if we take up another point instead of B, we take a point symmetric respect to the x-axis, we get the same alpha. But we don't want that. In this case, we want this angle here. So if the y component is less than 0, the alpha angle is equal to 2 pi minus alpha. Okay, enough theory for today. So let's create a point somewhere on the plane. And we want a circular motion around the origin. So let's create a rectangle. Let's define our parameter t equal to time for now. Now, our position vector is equal to the x component, y is 0 because we are on the plane, and z is equal to p at z. So our radius is equal to the length of the position vector, basically the distance from the origin. Now let's calculate the alpha, the angle. So our axis is equal to 1, 0, and 0. The dot product is equal to dot between pose and axis, and alpha, our angle, is equal to arc cosine of the dot product divided by the length of the position vector, which is radius. And now we can write the equation. So position is equal to cosine of t plus alpha times the radius. The y component is 0, and sine of t plus alpha times the radius. And now we should have a circle around the origin, starting from the current position of the particle. So if we put down other points in different positions, we have a circular motion around the origin. The only thing missing here is the case in which z is less than 0. Let me show you what I mean by that. If we create another point with z negative, as soon as we click on the attribute wrangle, it switches on the other side. That's because we didn't... if p at z is less than 0, alpha is equal to 2 times pi minus alpha. And now we should work correctly. Okay. Nice. Now let's create a polyline. So we can start creating an attribute ID for each particle. I at ID is equal to the ptnum. If we use a trail node now, let's say 25 for now, and a add node to create the polyline based on the attribute ID. And now we have lines, we can control the length. Okay. Now, instead of using the add node to create points, let's create a sphere with a radius of 3. Let's scatter some points here. Let's start with 10 points and use this one instead. We have to change just a little bit the script, because now the y component here is not 0, but is the current y position of the particle. So p at y. And we should have lines around the circle, around the sphere. Let me template the sphere. You see? Now for the vertical motion, the code is exactly the same. We just need to switch the axis. Let me comment out this part. Copy and paste. So we now want to rotate around the x-axis. So this one will be 0, P at y, the axis is 0, 0, 1, this is y, and now this should be, let me think, px is 1 and cosine here. Yes, okay. Now let's move the script inside a solver. Copy and paste here. Now inside a solver we don't need the time anymore, we just need a parameter speed, an increment, because the position attribute is updated by the previous frame. Okay, and we should have the same result. This is the ED attribute. Okay. So inside the script, let's define a parameter, a variable direction is equal to 0. 0 will be horizontal, 1 vertical. So if direction is equal to 0, we go horizontal. Otherwise, vertical. Oops. So everything should be horizontal right now. Okay. And the question is how to switch direction. So my idea is to create a noise attribute on the surface of the sphere. Well, first of all, let me increase the resolution here. Let's say 30 and 60. Okay. Attribute noise. Let's call it, this is a float value noise. Animated. Okay, maybe we can decrease the element size just a little bit. Okay, and now let me bring the noise inside the solver. So we can use the input number 2 inside the script. And we can say, take the near point with respect to my position and evaluate the noise at that point. Float noise is equal to 0.1 noise pt. If the noise is greater than 0.5, switch direction. Direction is equal to 1. And now we should have a switch. Yes, okay. Now let me increase the number of particles. And don't forget to reset the simulation. Okay, we have something. Obviously, we can play with the settings until we are satisfied with the result. And increase the number here. Okay, as you can see here, let me reset the point size. After a while, the points create clusters. And let's use 100 as a reference. So we can take this one and say time shift F plus 100. So we can start from this situation. Let's now create some energy moving along the polylines, starting with a resample. We don't need new points, we just need the curve view. And a wrangle. So let's create a parameter t, a variable t equals to time. And now energy will be just a remap of the curve view attribute, fit f curve view between t minus something and t from 1 to 0. Let me create the attribute. Okay, now the energy is growing along the lines. Let me remap. Let me use a ramp here. Something like this. Okay. Okay, now we have just one cycle. Everything is starting at frame 1 and with the same width, which is this one. So let's start creating a speed parameter that we can use to scale our time times speed. Okay, and let's also use the modulo here to have multiple cycles. So we now have multiple cycles. Okay, and now we can define few attributes per primitive to have a more interesting situation. So let's define let's create a primitive wrangle. We are going to create 3 attributes. Local speed, local width, and local shift. Fit, let's say random using the prim num plus some random number, fit 0,1 between the speed 0.5, 1.5. Change the number here. So the width 0.2 to 0.6, for example, shift from 0 to 0.8. And we need point attributes, so attribute promote from primitive to points, local underscore whatever. Okay. Now we have a local speed, so we have different speeds for different lines. We have a local width, so the tail will be different for each line. And we can also use the local shift plus F at local shift, so at frame 1 we'll have just something more interesting. Okay. The last step is to blast everything with energy below some value. This is a point group, let's say energy less than 0.1. So we now have out energy. We have lines. And we also have the sphere. And maybe for the sphere we can use a peak node to create a little bit of margin between the sphere and the lines. Just a little bit. Okay. So we can now create emissive materials and stuff and glow and so on to create the final shot. See you next time. Bye.